To analyze LTIC systems where LTIC stands for linear, time invariant, continuous time, we start by looking at how those systems can be represented in the time domain. LTIC systems can, for instance, be represented in the time domain by the input-output equation, which has n+1 terms on the left-hand side. This is the nth derivative of the output signal y of t plus the n-1 derivative of y of t weighted by factor a n-1 plus the next derivative of the output y of t weighted by factor a n-2 and so on up until the output y of t weighted with factor a0. This is equal to m+1 terms which depend on the input signal x of t multiplied with coefficient b0 and the first m derivatives of the input signal x of t, that is bm times the mth derivative of x of t plus bm-1 times the m-1th derivative of x of t, and all following derivatives up until b0 times x of t. It's important to know here that for LTIC systems the coefficients a and b are constants. In the time domain, LTIC systems can also be represented by the impulse response h of t. The term impulse response refers to the fact that h of t is the response or the output of the system when applying the impulse function delta t as input. When the impulse response h of t is known, the output of the system y of t can be obtained for any impulse signal x of t using the following equation. Y of t is equal to the integral between -infinity to +infinity of x of tau times h of t minus tau d tau. This is equivalent to the integral between -infinity and infinity of x of t minus tau times h of tau d tau. This is the convolution integral of x and h, and the shorthand notation is x of t star h of t.